Hello students, today we will continue to look at the Tamil Nadu 12th Board Maths Chapter 7, Applications of Derivatives. So we will be focusing on exercise 7.7, which involves the concepts of extremum points, that is maxima, minima, and then the concavity and convexity of the curves. And we look at some concepts and the important questions. So first, we look at the concepts that graph, which is said to be concave down at a point if the tangent line above the graph, the vicinity of the point lies above the graph. So this basically has the shape shown here. So this is concave down, and if the concave up is if at a point with tangent line to the graph lies below the graph in vicinity of the point, then it is a concave up curve. So this is the red portion which we see. So here we from physics we have also looked at like concave lenses and convex lenses. So we get some idea like concave means which goes down and convex is something which comes up in terms of the lenses. Now the definition in terms of differentiation is that let f of x be a function whose second derivative exists in an open interval I equal to a comma b. Then function f of x is said to be if f prime of x is strictly increasing on I, then function is concave up on the interval I. So here what we see is that the slope here, f prime of x is the slope of the tangent, it keeps on increasing. It's negative, it becomes 0 and then it increases. So there it is said to be concave up. And concave down is when the function f prime of x is strictly decreasing on I, and function is concave down on open interval I. So this is how it changes. So it is positive here 0 and then it goes negative. So it is concave down. The another test of concavity is that if f double dash of x greater than 0 in an open interval I, then f of x is concave up on I. So if f double dash x is greater than 0, like shown here, then it is concave up. If f double dash x is less than 0 on an open interval I, then f of x is concave down. So this will be using in the problems here. The next concept is the point of inflection. So the point on the graph where the function changes from concave up to concave down or concave down to concave up are called points of inflection. So how to find the point of inflection is that if f double dash c exists and f double dash c changes sign when passing through x equal to c, then the point c comma f of c is a point of inflection of the graph. If f double dash c exists at the point of inflection, then f double dash c is equal to 0. So this is the test we have for the point of inflection. Now, we have the second derivative test for the extremum points. That is, suppose c is a critical point at which f dash of c is equal to 0, that f dash of x exists in the neighborhood of c, that f double dash c exists. Then f has a relative maximum value at c if f double dash c is less than 0, and a relative minimum value at c if f double dash c greater than 0. If f double dash c is equal to 0, the test is not implemented. So this is basically like we have f double dash c less than 0 means it's a convex curve, so we get the maximum value. And when f double dash c is greater than 0, it's a concave curve, concave up curve, so we get a minimum value. So these are some sample functions which I wanted to show for discussion's sake. So we have x cube over here. So this is how the x cube curve works out. So we have on the negative first quadrant and the third quadrant. That is, so for the function y equal to x cube, on the negative x-axis we have a concave down or convex up curve, and the curve is concave up on the positive side. So x equal to 0 is a point of inflection here. When we take the inverse function of this, which is cube root of x, what we have is that this function basically is reflected about the line y equal to x. So we get this function, and this here we see that the function has concave up on the negative x-axis, it is convex on the positive x-axis. And here again we have a point of inflection where it changes from when the concavity changes. In comparison, when we look at the x square and x to the power 4 curves, so x square curve is always concave up, and even x to the power of 4 is always concave up. And we don't have any point of inflection here. We just have a minima point at x equal to 0. So following this, we look at the exercises. So in 7.7, we'll be looking at subsection 1 and subsection 2, and then question number 2, subsection 2. So for the first question is find intervals of concavity and points of inflection for the following functions. So the first function we have is f of x is equal to x into x minus 4 cube. So to differentiate this, we have to basically double differentiate and look for the sign changes in f double dash of x. So we have, using the multi-product rule, we are going to differentiate. So u is equal to x and v equal to x minus 4 cube. So f prime of x, we keep this as constant and differentiate x, get 1. And we keep x as constant and differentiate this one, get 3 into x minus 4 the whole square. So here I am taking out x minus 4 the whole square common outside, and in the brackets I have x minus 4 plus 3x. So here, while we simplify, what we get is x minus 4 the whole square into 4x minus 4. So I get 4 into x minus 4 the whole square into x minus 1. Now, if double dash of x is, finally, we differentiate this again using the product rule. Here we use x minus 4 square as one term and x minus 1 as a second term. So when we differentiate x minus 4 the whole square, I get 2 into x minus 4 and x minus 1. And I keep this as constant and differentiate the second part. So it's x minus 4 the whole square into 1. So here we simplify, what we get is 4 into x minus 4 and 2x minus 2 plus x minus 4. We get is 3x minus 6. So I take 3 common outside. So I get 12 into x minus 4 into x minus 2. Now you can see, first find the points of inflection. That is, the points of inflection occurs where f double dash of x is equal to 0. So that from this expression we know comes, this is a quadratic. So it is 0 when x equal to 4 and when x equal to here. And with this we divide the real axis into 3 intervals. So the real axis is between minus infinity to 2 is one portion, between 2 to 4 is another portion, and from 4 to infinity is other portion. Now to find out which is concave up and which is concave down, I have to substitute a sample point in these intervals. So in minus infinity to 2, 1 lies in that interval. So I put x equal to 1. and what I get is f double dash x is greater than 0. As this is negative, this is negative, negative to negative is positive. Now between 2 to 4, I have 3. So I can substitute x equal to 3. So when I substitute x equal to 3, I get 3 minus 4 is negative, 3 minus 2 is positive. So f double dash x is less than 0. And for a point in this interval that is between 4 to infinity, I have 5. So when I substitute 5, what I get is this is a positive value, this is a positive value. So we have the double f double prime to be greater than 0. So f double dash of x changes sign. So from this table we see that this is plus, f double dash is plus, so it is concave up. If it is minus, it is concave down. If it is plus, it is concave up. So f double dash x changes sign when passing through x equal to 2 and 4. Therefore, point of inflection are for we have to substitute x equal to 2 and 4. So for the first value, I substitute y equal to 2 into 2 minus 4 cubed, I get minus 16. And for the second point, I have f of 4, which gives 4 into 4 minus 4 cube is equal to 0. So the points of inflection are 2 comma minus 16 and 4 comma 0. So this finishes the that portion of the question. Now we'll move on to the next problem, which is f of x equal to sin x plus cos x. So when we have this function, I'm going to differentiate it first. First differentiation is that sin x we differentiate is cos x differentiated is minus sin x, and the interval is between 0 to 2 pi. When you double differentiate f, what I get is cos x differentiated is minus sin x differentiated is cos x. So to get the values where this is equal to 0, we have f prime equal to 0, and that when we simplify is when points at which tan x is equal to minus 1. So here we know from trigonometry that the tan x values is positive in the first and third quadrant, it is negative in these two quadrants. And if it is equal to, and that is usually has to do with 45 degrees, which has to do with 45 degrees. So we know some properties of tangents. So one point will be lying somewhere in this quadrant. So we use the pi plus pi 2 pi minus pi by 4, that gives us one value here. Two pi plus pi by 4, that gives us one value is 7 pi by 4. The other one is pi minus pi by 4. So this is actually not correct. So this is actually not correct here. So it should be pi minus pi by 4. So for just to refresh the memory, the tan x curve is like a falling waterfalls. It has this type of shape. It goes to plus infinity at pi by 2, and then it goes to minus infinity as at minus pi by 2. So we get the two values of, we get the minus 1 values at 3 pi by 4, and then at 7 pi by. So yeah, we use this. This is one way. The other way is we can use this identity that tan 2 pi minus x is equal to minus tan x, and tangent of pi minus x is equal to minus tan x. And we know that tan of pi by 4 or tan of 45 degrees is 1. So to get -1 and also -1, we have to substitute x equal to pi by 4. That is just to refresh the memory from trigonometry. We have the 4 quadrants. We can write it as silver teacups. That is, here all functions are positive. Here only sine function is positive. Here only tangent function is positive, and here only cosine function is positive. Anyways, we have identified the points of inflection. So now we divide the interval from 0 to 2 pi into these three values. That is 0 to 3 pi by 4, 3 pi by 4 to 7 pi by 4, and 7 pi by 4 to 2 pi. Now we have to find out the value of f double dash of x in this interval, in this and this intervals. At x equal to pi by 2, which lies in this, x equal to pi by 2 lies in this interval. So when I substitute f double dash of x, that gives us -1. And that is -1 because we have sine of pi by 2. We have minus sine of pi by 2 minus cos pi by 2, which gives us -1. Then we take another sample point in this interval. That is pi. Pi lies in this interval, 3 pi by 4 to 7 pi by 4. So that is basically shown here by the dotted line over here. It is the first interval in this circular coordinate system is here. This is the third interval, and this is the fourth interval. So in second interval, I take pi, so I substitute minus sine pi minus cos pi. So I get 0 over here, and minus of -1 is. Now the next one is the next point is somewhere in this interval between 7 pi by 4 to 2 pi. To find that value, I'm taking pi by 6 or 30 degrees. So f of 2 pi, so the double differentiate value at 2 pi minus pi by 6 is basically so this is f double dash of x. That gives minus sine 11 pi by 6 minus cos 11 pi by 6. So we know that in that fourth quadrant, sine gives us negative value, so it is -1 by 2, and cosine gives us positive value, and the value is √3 by 2 because it is 30 degrees. So it is related to the 30 degrees value. So here I have one, this becomes minus of minus plus, and this is 1 minus the √3. So note that the √3 is 1.732. So this value is negative. So going and putting that into this table, I have f double dash as negative here, positive here, and negative here again. So concavity wise, it is concave down here, it is concave up in this interval, and it is again concave down in this interval. Now to identify the point of inflection, we know that f double prime changes from negative to positive at 3 pi by 4, and from positive to negative at 7 pi by 4. So these two are the points of inflection, and to find them, I'm substituting 3 pi by 4 in this function, which is sin x plus cos x. So sine of 3 pi by 4 is 1 by √2, and cos of 3 pi by 4 is -1 by √2. So you get 0 over here, and at 7 pi by 4, sine of 7 pi by 4 is again 45 degrees, and because it is in this zone here, so it is a negative, sine is negative, so -1 by √2, whereas cos is positive, 1 by √2. So the sine convention we know, but also the value we know is related to 45 degrees. So I can get 0. So points of inflection are 3 pi by 4, 0, and 7 pi by 4, 0. Just to visualize, this is how the function actually is. This is not required for the solution, but I'm showing this for explanation's sake, that this the function f of x, it's a sinusoidal function, crosses at 3 pi by 4 and 7 pi by 4. Now the next question is that find the local extrema using second derivative test. And I'm going to solve the second portion, second subsection in this one. So f of x is equal to x log of x. If f of x is equal to x log of x, and we know that only log x is defined only for positive values of x. So x is an element in 0, infinity. Now f prime of, we do the first differentiation. So here I use the product rule, that I keep u equal to x and v equal to log x. So when I do u prime, when I do u dash, I have 1, and when I do v dash, I get 1 by 6, 1 by x. So u into v prime is x into 1 by x, and v into u prime is 1 into log x. So f prime of x is 1 plus log x. And we know the critical points, that is either maxima or minima, is given when the first derivative is 0. So the first derivative is 0 here. So we equate this and get log x equal to -1. So we get x equal to, due to the inverse of this, we get x equal to e power -1. Now we have to find whether we only have one extremum point. We have to find whether it's a minima or a maxima. So for that, I do double differentiation of this function again. So this gives 0, and the second part gives 1 by x. And I substitute x equal to e power -1. So what I get is, it's a positive value, because 1 by e power -1 is again e, which is positive. Therefore, it is a concave up, and it's a or a local minima from the second derivative test. Now to find the value at this, the y-axis value, I write f of e power -1. So what I get is x is e power -1 log of e power -1. And the property of logarithms, we take out -1, and I get -1 over here. And log of e to the base e is 1. So we have 1 by e into -1, and I get -1 by e. So the minima point is 1 by e, -1 by e is the minima point. So this finishes the solution, but for the sake of visualization, I have just drawn the function over here. That is, the function x is the dotted line over here, and log x is the function shown here. So the product of the two of them will pass through, will be defined, will start here and go to a minimum point and go in the positive direction. And here is the minimum point which we get. So I hope you understood the important questions in this chapter. You can contact me for any doubts related to this chapter, related to this exercise. உங்க எக்ஸ்பிளனேஷன்ஸ் தமிழ்ல வேணா சொல்லுங்க, அது ஏற்ற மாதிரி தமிழ்ல எக்ஸ்பிளனேஷன் தரேன். தேங்க்யூ.